Hi there, welcome to another presentation of our e-tutorial series. My name is Charles Gosfani Msipa. Our topic today is Newton's law of cooling.
Okay, let's turn to our short topic of discussion today, which is going to be centered on what we call Newton's law of cooling. So the situation is as follows. We all know that if we have got an object, let's say an object which has been heated up, and we take it away from the heat and put it in a room temperature, we know naturally that the temperature is going to change. And obviously if the object is hot, we expect that the temperature, the room temperature or the surrounding temperature is lower than the temperature of the body we are exposing to the room temperature. Then we expect the temperature of the object to go down in a pattern which we can be described as some kind of exponential decay. So let's look at what Newton's law says. Newton's law says if we introduce a hot, in brackets they put cold. So if you can read this in this way, you can first of all read omitting what is in brackets. So in this case we introduce a hot object, and hot object is going to into a cold surrounding. We expect that to cool down. Respectively, if we take a cold object into a warm environment, it will warm up. So let's focus for now on a hot object being introduced to a kind of a warm, cold surrounding. So what does the law say? It says that if we take a hot object, put it in an environment which is cool, what's going to happen is that the rate at which the object cools down is proportional to the difference in temperature between the object and the surrounding. And the surrounding sometimes is, you will find it described as the ambient temperature. So what does this situation say? Once we talk rate, we know that we're talking about the differentiation. In this case, if we decide to describe the temperature of this body via a function of time, let's say y of t. So this will be the object temperature at time t. So but in this case we're talking about the rate of change of this temperature as the object cools down. Then we're talking of y prime of t, which is our rate of change. So this is the rate of change of the temperature. So that the law says this rate of change is proportional to the difference between the temperature of the object and the ambient temperature. In this case here, the surrounding temperature, I'm going to call it ambient temperature, and we write it here as denoted as a y sub a for ambient. So in other words, this the rate of change of the body, the temperature of the object is proportional to this difference. Like we saw before, this means that, or this is equivalent to saying, there exists a constant, let's say constant k, such that the rate of change is equals to k multiplied by y of t minus the ambient temperature. So now we're in the presence of a differential equation, and as you can see here, we see a derivative of order 1, then we'll call this a first order differential equation. This is the first order differential equation. So what we suggested was suggesting that differential equations have got what we call order, and the order of the equation is going to be derived from the highest order of the derivative which appears in the differential equation. And in this case, since this function is a function of one variable, and this is an ordinary derivative, so this equation is going to be called an ordinary differential equation, in short, ODE. So now what we need to do, what is our task now, having this equation? We know that our unknown is y of t, which will be the model which describes how the temperature of the hot object goes down. So what we need to do now is we have to task ourselves by solving this kind of differential equation. So what we can do now is transforming this equation, dividing both sides by our bracket here. We're going to get this kind of an expression, y prime of t over yt minus the ambient temperature, that is going to be equal to the constant K. So now, I think we've seen this before. Once we've got this differential equation like this, and our target is to find our function y of t, we need to introduce the integral sign on both sides. So what we're going to do here, I'm going to write here, this is equivalent to saying the integral y prime of t dt over y of t minus ya is equals to the integral of k dt. So what we need to do now, we need to proceed by integrating on both sides, but first of all, let's simplify this integral to a kind of a standard integral by using our methods of substitution. So what we can say now, we can say let u be equals to yt minus ya. Remember, this ambient temperature in this case is taken to be constant and is also taken to be less than the temperature of the object. So we have that this yt minus ya is greater than 0. So now here, continue with our substitution. We will say du dt is equals to y prime of t, and the constant differentiate to 0, which this is equivalent to saying du is equals to y prime of t dt. I hope that is clear. So now, which means that now this term here, we have it in the numerator, we're going to substitute by du, and the denominator is u. Then we've got a kind of a standard integral, which is the integral du over u equals to integral of a constant k with respect to t. So now I think we're familiar with this now. So what we're going to do, and here we've got a constant, which is the derivative of a linear function usually. So integrating this, we're going to have this equivalent to ln of u equals to kt, which is the integral of the constant there, plus a constant c. So as you can see now we're close to getting to what we want. What we can do now, we can do backward substitution here, substituting U by Y of T minus the ambient temperature. So this is going to be ln of Y of T minus the ambient temperature equals to KT plus C. You note that I put brackets here because we usually put brackets here, absolute value here to take note of the fact that the ln function does not accept negative arguments, but in this case we've got this equal to that, so we can even take this as our usual brackets, but in this case it's fine like that. The next thing to do now is to apply the exponential function on both sides here, which will give us e to the power ln y of t minus ya. I'll just use my ordinary brackets there because of what I've just said, equals to e kt plus c. Now we remember that e, the exponential function, natural base, and then this function ln are inverse functions, and we know that if you compose a function and its inverse, we normally get an identity function. In this case, it will be an identity function on x, which will give us x. Now our role of x here is played by y of t minus the ambient temperature. So I'm going to have this as y of t minus the ambient temperature equals to, on the right hand side you can use the rules of exponents because this can reduce to e to the power c multiplied by e to the power k t. I hope that is clear. And here we can actually choose to set this c, so e to the power c equals to a0. Then we can rewrite this as a0 e to the power kt. Now what we can do now is to now make our yt subject to the formula, and we can do that by adding on both sides ya. So adding on both sides ya, we get this function being y of t equals to a0 e to the power k t plus y a. So now this becomes our general solution for this type of equation which we've got there, and this is a model for which describe how a hot object introduced to, let's say, for example, a room temperature environment will go down. In other words, the hot temperature at any time y, at any time t, it will be a times kt equals 2 plus the ambient temperature. So in this case, of course, since we expect this temperature to go down, it means that here k will be a negative, it will be negative. That is, if the object was hot, if the object was hot, that k would be negative. But if it was cold and it had to, the temperature to rise because of the ambient temperature, obvious here, the opposite will happen. Our K would be greater than 0 because it will be indicating the rise of temperature according to what the ambient temperature is. So I think after this, what we do now is to take particular examples of this kind of situation and solve some problems. Okay, maybe before we proceed to solving particular examples, let's just go over the whole process of solving this type of differential equation and try to tie some loose ends here and there. So the problem is that this one, it's based on this scientific principle which we call Newton's law of cooling, which states something which is almost obvious to all of us, that if we take a hot object and introduce it to an environment which is cooler, the hot object will cool down. But now this law states that the rate of change of that temperature as the object cools down is proportional to the difference of the object temperature and the ambient temperature, which we've denoted here as YA. A for ambient, which is the surroundings. So saying the rate of change, once we talk of rate of change, we all know that we're talking about the derivative of the function. So we write here y prime equals to k multiplied by yt minus yk. This is what is expressed by the fact that this rate of change is proportional to this difference. It simply means that there exists a constant k such that this equation is true. And we repeat here, highlight that this is a differential equation because of the appearance of the derivative y prime here in this equation, and it's a first order derivative. Then we call this a first order differential equation. And take note also the fact that this is a function of one variable, and this is an ordinary derivative, so this is what we call an ordinary differential equation. And solving this type of equation means finding the unknown function y of t. So for solving this, we put exactly at the equation there by transforming it this way. I hope you can see that we've got this expression expressed in terms of yt, both yt and the derivative of yt, and ya, which is the ambient temperature, equals to that constant there. So to find yt, we would need to integrate the expression, which detects that we should introduce integration on both sides, which we learned this way. And now we can see that we got an apparently complicated integral there, which we can simplify by reducing it to a kind of a standard integral by using the method of substitution, whereby we let our u equals to yt minus ya. So differentiating du dt, we get that it's equal to y prime, and the ya, since a constant ambient temperature, is going to be, this rate of change is going to be 0. So we got that. Then making du subject formula, we get that du is equal to y prime by dt. So now we use this expression to substitute that numerator, then we get an integral like this, which is a kind of a simple standard integral, which we're familiar with. So integrating on both sides, there we get ln of u, and this side, on the right hand side, we get kt plus c. Now we use the absolute value sign here, just to emphasize that fact that the ln function does not accept negative arguments, but noting that yt minus a is greater than 0, we could have also used the ordinary brackets here, which we've actually used in the second line here, by introducing the inverse function e, the exponential function inverse to ln, because of this fact that the composite of a function and this inverse is an iterative function, in this case, the iterative function of x, and now our x, the role of x is played by this difference here, which comes out here as yt minus the ambient temperature equals to a0 e to the power kt by setting e to the power c equals to a0, which is a parameter there. Then, now subtracting on both sides, adding on both sides ya, in this case here, adding both sides, we should say there, adding both sides ya, we arrive at this expression, which is actually the function of time which describes how that the body temperature or hot object is changing. And we also remark here, make a remark here that we should note that if the object was hot, is going to cool down, then this K must be less than zero to indicate decay. And if on the other hand, if we were considered a cold object introduced to a kind of warmer environment, we would have our K greater than 0. So I think after this now, you are ready to apply this kind of model to solve some particular problems. Otherwise, for now, I would like to say thank you for listening.